Yeah, sure. I do have a disclaimer to give. So all of this talk was stolen from an essay I read called The Mathematician's Lament. Almost all of it was stolen. But then I started coming up with some original ideas. And one of the original ideas I had was this quote: "If you want to build a ship, don't drum up the men to gather wood, divide the work, and give orders. Instead, teach them to yearn for the vast and endless sea." Right? This is like a bomb quote. This is like a really cool quote. And then I got the book called The Mathematician's Lament, which is like a little bit expanded. And this quote was at the very beginning. It was really like ridiculous. So my disclaimer is I stole almost everything except I didn't steal this quote. This was parallel thinking, and that's really important. Okay, anyway, thanks for coming to my math talk. My name's Wei. Let's read this quote again, just so it sinks in. "If you want to build a ship, don't drum up the men to gather wood, divide the work, and give orders. Instead, teach them to yearn for the vast and endless sea." So that's what this talk is going to be about. I'm going to try to give you a taste of the vast and endless sea that is math, right? And the problem is, a lot of people, I would say the vast majority of people, don't know what math is. And this talk is all about what math is deep down. Okay, so imagine if you didn't know what painting was, right? And you came to me as someone who knows about painting, and you were like, "Hey, Wei, why is painting cool?" And I'm like, painting's really cool because it's super useful, right? Because like visual design is a key aspect of our culture, right? We live in an advertising economy. And so if you get really good at designing stuff visually, you'll be able to advertise to people and you'll be able to sell things. Or because advertising in general is in such high demand, you'll also be able to make money as an advertiser and like sell other people's stuff. And I'm like, oh, okay, that's cool. That's cool. I can use it to survive. But I'm like, not only that, painting and visual design can also be very persuasive. So you can get people to like vote. That's another cool feature. You can use it to literally change the world. And some of the most effective political campaigns have been through like visual stimulus, through painting, right? And you're like, oh, wow, that's really cool. And I'm like, not only that, if you get really, really good at painting, you could, there are these things called art auctions. And at art auctions, paintings can go for like hundreds of thousands of dollars, sometimes millions of dollars. So if you get really good and really, really lucky, you could become a millionaire overnight. And you're like, oh, wow, this is really compelling. And I'm like, no, but I'm not even done yet. There's even more. Not only is painting super useful, it's actually everywhere around you. No matter where you look, you see paint, right? The walls of your house are painted. If you go on the street and look around, fire hydrants and street signs and cars are painted, right? This is all painted. If you go to the store, you'll see like bags of bread. This is kind of like painting, right? This is like painting. Your clothes are dyed. That's kind of like painting, right? These are all the reasons painting is so cool and compelling. And you're sitting there and you're like, oh, thanks, Wei, I get it now. I know why painting is so great. And then you go about your business and we never speak again. And then you're like wandering around and you see this. And you're like, whoa, what is this? This is beautiful. This is gorgeous. This is stunning. And someone tells you, oh, it's a painting. And you're like, wait, what? This is a painting? I thought paintings were cool because they were useful, because you could like advertise and because it's like on your house. That's why I thought paintings were cool. And then you see this. And then you see this. You see this. And you see this and 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 this. And you're sitting there looking at all this stuff. And you're like, huh. I feel like that guy I was talking to earlier didn't do a very good job of explaining why painting is so cool, right? Why did he try so hard to convince me painting was cool by saying it's useful and it's everywhere, right? He didn't need to say anything at all. He could have just shown me these things and I would have understood, right? Isn't this a much more compelling explanation for why we paint? Namely, it's beautiful, right? This is why we paint. And actually, on a deeper level, I want to say the beauty of painting is actually the deep reason that undergirds the other two reasons, right? We as human beings crave beauty, aesthetic harmony, and exploration, and raw self-expression, and creativity for its own sake, right? This is what painting is. Painting is the existential struggle for meaning alleviated by form and color, right? And it's the same with math, right? This stuff right here is why we do math. But the problem is we never see this, right? In math, this is all we ever see, right? In school, we learn that we do math because it's useful, right? You can use it to like get engineering jobs and make a lot of money. And it's also everywhere around us. Like it's in your smartphone and you use it to build bridges or whatever, right? This actually does math a deep disservice because the actual reason we do math is because of the stuff I was saying before. It's because of the pure beauty and the self-expression, right? Now, the problem is the beauty is kind of hidden from us because math is like different from painting. Right? In painting, we care about the final product. That's really what we care about. The word painting itself suggests that, right? It's both the noun and the verb. That's what we care about in painting. But math isn't really like that. So math has a different kind of beauty, right? So imagine if I was trying to get you super excited about some activity and I showed you this picture. And I was like, isn't this activity so cool? Like, look at this. Isn't this so hype? And you're just like, I don't really get it, dude. This is just a guy standing there, right? What's so exciting about this? And I'm like, no, you don't get it. Like this right here, this is what you need to care about. This is so essential. This is like the most important feature of our world. And you're like, yeah, I'm not really getting excited about this, man. I'm sorry. Right? This is all you ever see in school. Because in school, what we care about is getting the right answer and like finding the right solution, right? This is not what math is about. Math is not about the final product. Math has a kinetic, dynamic beauty. The beauty is in the process. It's not until you see the process by which we arrive at the solution that you see the beauty, right? I have a lot more to say about this in part 2, but for now, just understand that math is not about a final product. It's about the process, right? So in that sense, it's kind of not like painting, but on a deeper level, it's actually not like any other form of art. Math is the purest form of art there is, right? And the reason I say that is because every other form of art has constraints. You have limitations. For example, in painting, you're constrained by like your canvas or your brushes or the paints you have to work with, right? In music, you're constrained by the sounds your instrument is physically capable of producing. In dance, you're constrained by how the human body is capable of moving around. Math isn't like that at all. What I mean when I say math isn't relevant is that there's nothing less connected to tangible physical reality than math. Math is pure imagination and creativity and self-expression for its own sake. And that's what this picture is going to symbolize. Math has a profound irrelevancy, a lack of connection to the real world. And that has so many interesting consequences. And that's what this talk is going to be about, right? Now, there's a problem with this. There's a problem with this limitless freedom. And in order to understand why limitations are actually good, we have to understand the nature of creativity. So what is creativity? This is like quite common saying. I don't know if you've heard it, but creativity is sparked by limitations. So limitations are actually good because they help us be creative. So my example is, imagine if I gave you a bunch of wood, right? And the wood like looked like this. And I'm like, okay, here's some wood. Go have fun with this wood. You just like kind of randomly move the wood around or whatever. I don't know what you would do with the wood. But if I told you this was a chess set and then I gave you the rules of chess, in other words, if I gave you limitations for how the pieces can move, suddenly you get ideas, right? Suddenly you have opportunities to express yourself, right? That creativity is born of limitations. Why is that? It's because limitations provide opportunities for problem solving. And we as humans love to solve problems. So the limitations are actually good, right? There's something to latch onto. But because math is completely disconnected from reality, and actually, I should say, reality itself has limitations, right? Everything we do, everything we come into contact with, there's like barriers and obstacles that prevent us from doing these things. Math isn't like that, right? Math is like being in the middle of the ocean with no landmarks anywhere around you, right? Imagine you're just in a vast expanse with no islands, nothing to look at. It's just a vast empty horizon, right? You have no idea where to go, right? So the question is, if we're in this realm, this domain of pure imagination, how do we get this island? Where does this come from? Like, how do we get this? Right? And this is going to be one of the core aesthetic principles of math, because it's so hard to like operate creatively when you have no limitations. We are guided by a core aesthetic. It's the aesthetic of simplicity. Okay, so this is what we care about in math. This is what is going to undergird all of our exploration, is making things as simple as possible for ourselves, because otherwise we have nothing to cling on to. Okay, so let's do some math right now. I want to think about the simplest possible thing I can think of. So here's an example of something really, really simple. This is a rectangle. Now, this rectangle alone is beautiful. This rectangle is beautiful because it's perfect. Like perfection like this doesn't exist in the real world. Stuff in the real world is made up of like atoms, and the atoms are jiggling around, and measuring stuff also is really hard, and like cutting stuff into like perfect rectangles is really hard, right? There's always a degree of error, but in math, it's perfect. Why is that? It's because math isn't relevant, right? Math has no connection to reality, so this can be perfect because I declare it to be so, right? So I'm really fascinated by this perfect thing I've made, and I want to explore it. I want to like learn stuff about it. So I need to do a little bit more stuff. So I'm going to pick a random spot on the top. Let's pick that spot right there. Doesn't matter. And I'm going to connect the corners to this spot. Okay. So now notice I've made something. Right now I have two things. I have this rectangle, but I also have this triangle inside the rectangle, and these two objects exist in some kind of relationship to each other. And I'm curious about what that relationship is, right? So I want to ask, how much of this rectangle does the triangle take up? Is it like a third? Is it like a half? Is it like a little bit less than half? Is it a little bit more than half? Is it like 2/3? I don't know, right? But more than that, I'm not really interested in how much it takes up. I'm more interested in the explanation, the process of how I get to that answer. Remember, math is a dynamic, it's a kinetic art form, right? So I asked this actually to someone on the plane. I was doing this math question, and he gave a really interesting explanation. He said it's like a little bit less than half. And his reasoning for that is, if you connect this corner to this corner right here, that's exactly half. And so if you take this corner and like walk it back, you're like peeling away some, so it's like less than half. And I thought that was a really interesting explanation. And as it turns out, it's not quite right, but that doesn't matter, right? The process of discovery is what we care about. So maybe think about this. Don't think about what the answer is so much as how you would explain it, right? What is the process by which you would convince someone as simply as possible? And I think I can do it with like no words at all. I can do it with a single line. So this is the line right here. This line right here is the beauty. This is the aesthetic of simplicity and clarity and precision of math. This in math is what we crave. This is elegance, right? So maybe you don't get it. If you look on the left side of the line, this diagonal cuts the rectangle perfectly in half. On the right side, it's also cut perfectly in half. So if both are cut perfectly in half, then the triangle must be half of the whole thing. Right? So this is the beauty of math, the ability to explain things with such precision and clarity and simplicity. I colored these in, right? So maybe it's a little bit more clear now. You can see that this is half of this, and this is half of this. Right? And other questions come to mind now. Like, what about other shapes, right? Like, is this unique to rectangles? Can I do this with other stuff? What if I pick 2 spots on the top? What if this is like a 3D object? How does this translate to more dimensions, right? I'm curious now. I've made something and I want to push the bounds. I want to explore like all of the complexities of this very simple thing I've created, right? And why am I thinking about this, right? Why do I care about this? It's not that it's going to be useful. It's not that I'm going to use it all the time, right? I'm never going to use this. This is never going to be used in my day-to-day life. I'm doing this because I am a curious person, because I want to learn about the world, because I want to express myself, because I want to be good at explaining things to myself, right? So that's what this is going to represent. This is going to represent the aesthetic of simplicity and clarity and precision when your explanation perfectly fits exactly what you want it to. Right. And notice something else. I don't care about the answer. The answer actually doesn't matter at all. I would have been just as satisfied if the triangle took up a third of the rectangle or a quarter of the rectangle. That actually doesn't matter. Okay. What I care about is the explanation and how simple and refined I can get that explanation. Okay. So that's the end of part 1. Maybe that triangle thing wasn't very compelling to you. Maybe you actually don't care about stuff that has no connection to reality. That's fine. I'm not really that into yodeling, right? Not every art form is for everyone, but at least I'm hoping you'll understand why I like math, right? So, just as a review for part 1, we talked about how math is kind of like painting in that we do it for aesthetic harmony, but we also talked about how it's kind of not like painting because it's a dynamic art form, it's kinetic, and we talked about how it isn't relevant. It has no connection to reality whatsoever. And part 2, we're going to expand on this. We're going to talk about how the deep irrelevancy of math actually loops all the way back around and causes math to be the most relevant thing in the world. I think that's really interesting. And we're also going to talk about how math is deeper than poetry. So here's a quote from a famous mathematician. "It is impossible to be a mathematician without being a poet in soul." Okay, so that's the end of part 1. If you weren't really into that, you're free to go as promised on the poster. But I'm hoping you'll stay around for part 2. So feel free to head out. I'm going to go on to part 2. Okay, so let's talk about how we learn math in school. This is how we learn math in school, right? Susan starts with some number of apples. The number of apples she has doubles. Then she loses 4 apples. Now she has 8 apples. How many apples did Susan start with, right? This is dog shit. This doesn't matter at all. This has nothing to do with math. This is like if I tried to get you to care about painting by like blindfolding you and having you listen to the painting, right? I'm never going to use like anything like this in my life, right? There's never going to be a situation where I don't know how many apples someone has, but I do know how many they have after it. Like, this is absolute garbage, right? This is how teachers try to get you to care about math. And it's not their fault, right? I'm not blaming teachers here because that's also how they were taught, right? This is what they think math is. This is how people try to make math cool, right? This is why math is actually cool. Math is actually cool because it's like poetry, right? So compare these 2 expressions. On the left, we have this expression: double a number, then subtract 4. The result is 8. What was the number? I kind of narrowed it down. I deleted some words to be a little bit more fair. And on the right-hand side, we have this: 2x minus 4 equals 8. So if we count the number of symbols on the left, we get 65. If we count the number of symbols on the right, we get 6. This is the beauty of math. This is why math is like poetry, because it can be so incredibly expressive, right? So here's a line of poetry I really like. It's in Arabic, the Sufi poet Rumi: "You are not a drop in the ocean, but the entire ocean in a drop," right? So much complexity and nuance can be conveyed with such few, like such little language, right? This is why math is beautiful. This is why algebra specifically is beautiful. The stuff on the left, that's like eye bleed, right? I never want to look at that. I never want to think about that. This is absolute garbage. Get that out of my sight, right? Now, here's the thing. It's like poetry, but it's actually deeper than poetry. And to understand that, we have to really understand the structure of math. And not only is math not like poetry, it's also not like history or physics or painting, right? It has unique features. There's a dividing line where math uniquely stands that makes it unlike every other art form and discipline. And so the way to visualize this is I kind of visualize all the other art forms and disciplines as like a low wall that is very wide. Okay. So notice something about this wall. If I take out this brick right here, that doesn't really affect this brick over here. Right. So what I mean by that is in history, if I don't know anything about the fall of Rome, I can still like know a lot of stuff about World War II. Right. Not knowing stuff about one thing doesn't stop me from knowing stuff about other stuff. Right. Or like in poetry, if I don't know a certain poetic device, or if I don't know a certain word, that doesn't stop me from knowing lots of other words. In physics, if I don't know like how classical mechanics works, that doesn't stop me from knowing stuff about like electromagnetics, right? In painting, if I don't know one technique, like if I don't know how to work with a sponge, that doesn't stop me from working with a brush. This is fundamentally different from how math works. Math is like this. Math is like a very thin, tall wall. So if I take out this brick right here, the entire wall is going to collapse. It's going to be devastating, right? Now, this is why math can be really hard, because if you're missing a single brick, the entire thing is going to fall down. Now, why is math like this? Why is math different from all the other disciplines? It's because math isn't relevant, right? In the other walls, bricks are in this wall because they have to be in this wall, right? So if some random historical event occurs, I have to slot in that brick because I'm beholden to reality, right? Physics has all kinds of like weird numbers, like the gravitational constant, right? That I'm slotting that in because I have to slot that in. Language, right? Language is really weird, right? Language has all kinds of aberrations and it follows weird rules because like some Sumerian dude grunted like 4,000 years ago or whatever. And that like complex geopolitical and socioeconomic factors cause that to evolve into the words I'm saying today, right? Math isn't like that. Every single brick in this wall is there by choice. And that's incredibly powerful. That's incredibly compelling. Right. So this is where math loops around and the irrelevancy of math becomes deeply relevant. Right. Every single brick here is there by choice. Right. So math is the aesthetics of simplicity and explanation. Right. So as it turns out, if you get really good at explaining things with clarity and simplicity, you can like predict diseases. Right? You can predict financial markets. You can predict ecosystems. You can make smartphones. You can make satellites and bridges. You can understand the structure of music and art, right? And it's also why math is like a deeply global language, because it's not beholden to real world constraints. It isn't relevant. It transcends politics and culture. Right? Every brick here has survived thousands of years of scrutiny and rigorous explanation, right? So I find this very beautiful. I find it beautiful how this deep irrelevancy actually loops all the way around and causes math to become the most useful thing in the world. And also, on a side note, this also explains why, like, people don't know how to teach math, why people don't understand why, like, what math is. I think firstly because like it's really hard for us to grapple with something that's so profoundly irrelevant. But secondly, like this paradox, how the relevancy of irrelevancy manifests is really hard for us to grapple with. And because math is so useful, power structures have kind of glommed onto it and stripped bare all of the beauty and the aesthetic harmony we're looking for. Okay, so how do we design these bricks? These bricks are not like normal bricks, right? So think about tools we use in day-to-day life, like a hammer. Right? A hammer is beholden to constraints like the size of your hand or how much weight you're comfortable lifting, right? Or the materials you have at your disposal. But In math, we have no constraints. We are free to design tools that solve our problem perfectly. This is another thing that makes math so cool, right? And as it turns out, as we start designing these tools, these scalpels that perfectly solve exactly what we need, the tools kind of start taking on lives of their own, and they start doing all kinds of incredibly weird, unpredictable stuff. So if you're curious about that, I'll get more into it in part 3. Okay, so let's talk more about this poetry. Every single one of these symbols is a design element, and you might not feel that. You might not like feel the full weight of that expressed because it's like super basic. We're fully immersed in it, so we don't see it. So let's zoom in on a single design element. Let's just look at this design element. This design element is beautiful. It's so powerful and compelling and expressive. And you might not feel that until you see something like this, right? This is dog shit. This is so hard to work with. Like, this is really confusing. I'm getting really confused looking at this, right? Contrast these two things, right? This is like poetry. This is like eye bleed, right? And incidentally, why did I choose Arabic for this poem? It's because these numerals are the Hindu Arabic numerals that were invented during the Islamic Golden Age, right? This design element is so good. We made it hundreds of years ago, and we're still using it to this day. But it wasn't always like that, right? It actually took thousands of years of innovation and progress to reach this design element, right? Before we had this, in books, even after we had this in like math books, would write out problems like this. Like we would have the eye bleed. Like every book would be like this. Like that's just so terrible, right? That you can see, this symbol right here is emblematic of progress and like the deep beauty of math, the relevancy of irrelevancy. But something you might be missing is that this is not the only way to write this, right? This is actually just some random like straight lines. This is an aesthetic choice. And as it turns out, there are tons of different ways we can express the same thing. And by writing it differently, we can reveal new patterns and new understandings, right? So here's a new way I can write 4, right? And here are some other numbers, right? And this might seem like almost childish to you or basic, but as it turns out, if you write numbers like this, you will get vastly different insights. This is a new aesthetic choice that's going to reveal new harmonies. Okay, so play around. I'm playing around with these numbers, right? And I notice something. I notice patterns. I notice that for some numbers, I can write them like this. So some numbers I can write in like 2 perfect rows. And I like this. This is pretty, right? This is symmetrical. But other numbers, I can't really do that, right? Other numbers look like this. And I kind of don't like this as much, right? There's like this weird little part that's like sticking out, right? I kind of wished that all numbers looked like the top part where it's like perfectly symmetrical and beautiful, right? So I'm like, I'm not really happy with this. But then I like play around with the stuff on the bottom and I notice something. I notice that if I combine 2 things on the bottom, I will get something from the top. And that actually works every single time, right? So I can do it with these 2, right? These 2, and suddenly I have the symmetry I crave. I have the pattern and the aesthetics I crave, right? It's kind of like the parts that are sticking out, like cancel each other out, right? Like 2 things that are not symmetrical fit together perfectly and become symmetrical. This might be a bit easier to see with rotation, right? So there it is. See, this is like a puzzle clicking into place, right? I love this. Now I'm more fascinated by the bottom row than the top row. I'm like, wow, this bottom row has all kinds of hidden patterns I can find, right? So I'm like, what other patterns can I discover, right? So now I'm curious about the bottom row. And I'm playing around with the bottom row and I discover something really cool. I discover if I combine the first 2 things, I get this. If I combine the first 3 things, I get this. If I combine the first 4 things, I get this. This is beautiful. This is symmetry, right? And actually I can take it a bit step further. What if I just took the first thing by itself? I get this, right? These are like somehow perfect in my mind. There's a symmetry that even transcends the symmetry of what came before. Right now, I'm really curious about this. I'm like, does this go on forever? What if I just like kept doing this forever? Would it just keep going? And as it turns out, it does keep going. But this wouldn't be a real math talk if I didn't make the most overused math joke of all time, right? So I'm sorry for making this joke. I'm not even going to say it out loud. But I'm curious, right? Like, what do you think about this? Does this go on forever? Spoiler, it does go on forever, right? But again, I don't care about the answer of whether it goes on forever or not. What I'm curious about is the explanation. And as it turns out, there are tons and tons of different ways to explain this that have their own aesthetics, right? You can make aesthetic choices to explain this pattern, right? So what I want is like emails. I want people to figure out how to explain this as simply as possible, right? This is where the self-expression comes in. And what I want the most, what I crave is the simplest or the most beautiful explanation, right? You get bonus points if you use no words at all. If you can only use pictures to convince me, or if you think of stuff like I haven't thought of yet, that's what's really exciting to me. Okay, so that's the end of part 2. We talked about more consequences of irrelevancy, right? Why the irrelevancy of math causes it to have this like very tall, narrow shape, and why every brick has to be here by choice, why the irrelevancy loops all the way around, right? We talked about how it's deeper than poetry. We talked about how the tools are perfectly designed to do exactly what we want them to do, and also how those tools like take on lives of their own and they become almost mystical, right? And so in part 3, we're going to really go deep here. So this is a quote you're going to want to remember for part 3. There is nothing as dreamy and poetic, nothing as radical, subversive, and psychedelic as math. Because as it turns out, if you have no constraints to reality, then the things you can think of are so wild and ridiculous that it's peerless. There's nothing else like this, right? Like the weirdest stories you can imagine have nothing on math. You're going to want to remember this quote because there's going to be a part where you like think you get it, but then it's going to turn out to be even weirder than you think it is. Unless you've seen Cantor's diagonalization proof, then you won't be surprised at all. Then it'll just be totally rote, I guess. But if you stay to the end, I have one more interesting math question for you. Okay, so I love this poem, right? This is so expressive and elegant, and we haven't been able to do better than this for hundreds and hundreds of years. Is there another poem I could write to express this? Okay, think about that. I want something radically different. I want something that like fully pushes the boundaries of what's even possible, right? So maybe think about how you would express this idea. And here's what I have. Okay, so this is an entirely different kind of poem. This poem is so like deeply weird and expressive as well. And maybe you don't really get what this is. That's fine, right? You don't really need to understand what this is. What I'm telling you is that this is kind of like this, except it's way more like sophisticated a tool, because not only is it this, it also, like if you change this 8, no matter what you change this 8 to, there's going to be a dot on this line that represents that. That's really cool, right? So now I'm not just talking about this one poem. I'm talking about almost every poem that is possible to write while preserving the left side, right? So this is like an infinite number of poems. This is like an infinite collection of poems. And I'm curious about this, right? I'm curious like about the numbers thing. I want to see like the consequences of making a tool like this. But the problem is this is like super complicated. Right, this is too complicated. I can't think about this. I need things to simplify down, right? Remember, I'm driven by the aesthetic of simplicity. So let's simplify, let's get rid of this, right? So this is like a little bit better, right? I got rid of that line and the dot, but this is like still too complicated, right? I really need to drill down on something I can understand. So what about this? Okay, this looks pretty good, right? Like I can count. And so I can see 1, 2, 3, 4. So counting's pretty cool. So I can do that. But honestly, this is still too much to look at. So we're going to really zoom in on this. This is what I'm deeply curious about. This arrow, the consequences of this arrow. What does this arrow mean? That's what I want to know. So what I really want to know is what forever means. Right? I'm curious, like, can I just keep counting forever? Is it possible to do that? And what happens if I just say yes? Right? What happens if I say, sure, I can just keep counting forever? What does that mean? Right? Now notice this isn't relevant, right? In real life, it's not possible to have an infinite collection of objects, right? That's fine though, because math is completely unmoored from reality, right? So I'm like, what does it mean to have an infinite collection of things? Well, I just keep adding stuff to this side, right? I just keep adding stuff over and over again. So now I'm curious about that. I'm like, okay, what if I add stuff to the other side? What if I add like something to the other side? Now it looks like everything's kind of shifted over. And I'm curious about how these two things relate to each other, right? In math, we care about relationships between the weird stuff we make, right? Now I'm curious, are these two things the same size, right? I would never ask this question in reality, because in reality, if you add something to a collection of objects, there's just more objects, right? That's really obvious. But here, it's not so clear, right? How do I know if two things are the same size? Normally, I would just count them, and if I get something different, I would be done. But I can't really count them, right? Counting is what I'm trying to explore in the first place. So I need to design something. I need to make a tool. I need to radically like redefine what it means for two things to be the same size. Okay. So here's my idea. This actually isn't my idea. This was come up by people way, way smarter than me hundreds of years ago. So I have two groups of things, and here's how I'm going to declare two things to be the same size. These two groups are going to have the same number of things if for every object here, there's exactly one object over here, and the same is true in reverse, right? So in other words, if I can draw like these lines, so this line connects exactly one thing over here to exactly one thing over here. This right here, these lines are how I am going to define two things being the same size. Okay. You can think of this like a map, like instructions. So for every origin here, there's exactly one destination you can get to on the other side, and vice versa. Okay. Now this is an aesthetic choice, right? Everything in math is an aesthetic choice. I could choose to say two collections are the same size for some other reason, but as it turns out, I really like this aesthetic choice, because if I make this choice, I get all kinds of incredibly beautiful and harmonious and simple results, and sometimes mind-blowing ones too, right? So it turns out if I define the same two things being the same size like this, it's pretty easy to see, I would say, that these two are actually exactly the same size, right? So I even lined it up for you, so it's pretty easy to see, right? And I can, if I want to, which, you know, maybe I don't want to, I can give this map a name, right? So this is the map. This is a set of instructions that tells you for every point here, there's exactly one point over here. Okay. And I'm like, whoa, this is already kind of weird, right? This is not like anything in reality. When I add something, it stays the same size, right? So now I want to push the boundaries of this. I'm like, what if I just take half of the stuff, right? So I just want to take half of the elements. So I'm going to skip over every other element. I'm just going to take half. I'm going to make a new collection. So surely these two things can't be the same size, right? Because I took, it's like only half of what I had before. But based on how I line this up, you might be able to tell these two actually are exactly the same size, right? Here's the map of how you get from the top to the, or from the middle to the bottom, right? You can kind of think of these collections as having this structure. This is how you visualize it. You like start and then you just keep going forever. Okay, cool. Now I'm really curious about what forever means. I want to know if I can push the boundaries of this. Okay, so let's stick with P for right now. and let's double up. So P has this kind of a structure. What if I staple an infinity to the back? Okay, so now Z has this kind of structure. Okay, so I want to make this really weird. Are these two things the same size? So maybe think about that for a little bit. What do you think? Right? Maybe it's not surprising because of the way I've set this up, but they are the same size. As it turns out, I can write Z like this, and I can make a map for everything on the top. There's exactly one thing on the bottom. Boom, like this. Right? So this structure is exactly like this. So this is like kind of weird, right? Like this structure actually isn't like this. It's kind of more like this if I write it differently, right? And here's the instructions, right? This is the map. This is a bit too complicated though, so don't worry if you don't get what this means. Okay, now I really want to push the bounds. Okay, so we have this. What happens if I take, for every two numbers, I squeeze another infinity in between them, right? So now I want to think about every possible fraction, right? So every possible fraction, I'm squeezing here, not only here, but I'm squeezing here. And because I'm talking about fractions, I'm also squeezing infinities between every one of these fractions, right? So I have infinities inside infinities, inside infinities, right? This is actually impossible for me to write down. Like I can't list them as neatly as I could before. So I have to make a shortcut. So I'm going to say this, right? This is what I'm going to call this new collection right here, because it's really hard to write down otherwise. So what do you think about this, right? This is like squeezing infinities inside infinities. When I first read this, I was like, yeah, these now are definitely different sizes, right? But as it turns out, they're not. It's actually still the same size again. And to me, this is where I get like a sense of awe, because like I never would have figured this out, right? This is so mind-blowing and weird. But as it turns out, if you write Q in a different way, you'll be able to get this structure again, right? So maybe think about how you would do that. And here's how very, very smart people did it. Okay, so I can make a table, right? So every possible fraction, a fraction is just some number divided by some other number, right? So if I have all the numbers on the top, and then I have all the numbers on the left, and then I just divide them, this is like every possible fraction there is. You might be looking at this and you're like, wait, this isn't really like this though. This is more like this, right? Doesn't it kind of go in like two dimensions? You just need to make one extra step, right? When I saw this in like whatever book I was reading, I was still not convinced. And it takes, in my mind, a real stroke of creative genius to see the next step of this puzzle, which is to draw this. So as it turns out, you can draw this line, and this line has exactly the same structure as this line, right? There's a one-to-one mapping here. Actually, there's not. There's like a slight detail I left out, and maybe you want to think about what that detail is. I did something sneaky here that I'm not going to tell you about because I want you to try to figure it out, right? But like something sneaky happened. But that sneaky thing doesn't really matter, right? At the end of the day, this is true. Like these two things are exactly the same size. So even when I peel these things apart and start stuffing infinities inside, it's still the same size, right? So you might be thinking, oh, I get it now, right? Forever just means forever, right? No matter what I do, every infinity will always be the exact same size, right? You should have remembered that quote from earlier, right? You're wrong again, because math is incredibly weird. Math isn't relevant. There's no connection to reality. As it turns out, there are forevers that are bigger than this. So you might be thinking, how do I make that? So this is where we get to Cantor's diagonal proof. This is probably my favorite proof in math. This is where I really experience that aesthetic harmony and simplicity. So what we've shown so far is that all of these things are exactly the same size. So now I want to think about, what about like all other numbers? So every possible number I can think of, even numbers that you can't write as fractions, right? Are these two things the same size? I might have given away the punchline. As it turns out, they're not. But how would you show that? How would you even start to show that, right? It takes, again, a stroke of creative genius, right? So we're going to do something called proof by contradiction. This is one of my favorite proof methods in math. So the way proof by contradiction works is you assume what you're trying to prove is false. And then, you assume what you're not trying to prove is true. And then you're going to get something that's ridiculous. You're going to get something that doesn't make any sense. And so what you assumed is actually false. So you're intentionally contradicting yourself. This is a really beautiful, aesthetically harmonious way to prove things. Okay, so how are we going to do that? So what I want to prove to you is that this is not the same size as all of these. So what I'm going to do is I'm going to assume it actually is the same size. So let's say all of these are exactly the same size. Okay, well, if they're all the same size, then I can just write them down like this, right? I can make this map, right? Both of these have the exact same structure. Now you'll notice I kind of had a hard time writing down R. So I just like wrote a bunch of random stuff. There's not like a place I can start, right? Because there's like an infinite number of points here. Okay. So this looks fine, right? This one goes on forever. This one goes on forever. What's the problem here? As it turns out, there is a problem here. So we're going to do something very clever. We're going to make a new number. And the number we're going to make is going to have a very specific procedure. So what we're going to do is we're going to take the first number of number 1. We're going to take the second number of number 2, the third number of number 3, the fourth number of number 4, and so on. Okay, so this is going to be our new number. So I have it here. This is our new number. And okay, that number actually isn't what I care about. I want to make a second new number. Oh yeah, this is how I got A. I want to make a second number that's called not A. And it's really easy to make not A. All you have to do is make every digit of not A different from that digit in A. So this digit is a 1. I just have to make this not a 1. This digit is a 4. I just have to make it not a 4. This digit is a 1. So I just have to make it not a 1. Right? It's pretty easy to do this. Okay. Now I want to ask myself a question. Does not A appear on this list? So is it somewhere on this yellow line? Well, let's think about that. Could it be the first one? Well, no, it can't be the first one because it's different in the first position. Could it be the second one? No, it can't be the second one. It's different in the second position. And it's going to be different from the third one and the fourth one. It is going to be different from every single other number on this list. So in other words, what I assumed before was false. This map does not exist. I thought I listed every single number before, but actually I found a new number that doesn't exist on this list. So actually these two things are not the same size. Okay. So I really want this to like sink in how deeply and incredibly weird this is, that you can have all of these forevers that are the same size, and then you can have this forever that's like not the same size. It's completely different. This is like a new thing, right? Okay, so that's the end of part 3. That's where math gets really weird and psychedelic. So part 3, we talked about this concept, right? This is the consequence of math being irrelevant, being a pure boundless expanse. The stuff you get is so disconnected from reality. It's so weird. It's like almost inexpressible except via the language of math, right? Here's a bunch of other weird math stuff. I don't really get much of this stuff, but this is like super weird stuff, right? Okay. So that's the end of the talk. I just want to say I stole all these ideas. If you want to embarrass me, read this book. It's going to be really embarrassing for me if you read this book, because you're going to see just how much of these ideas I just ripped straight from this book. This question is another one I ripped from this book. This is one of my new favorite math questions ever. I love this one. And I don't think I would have come up with the answer myself, but I want you to. So the question is very simple. What's the shortest line I can use to connect these two dots that also touches this line right here? Right? So let me give you some examples of potential lines I can draw. So like this, that's totally valid. Like that, that's valid. I could get real wacky with it. I could do that, right? But I'm interested in the shortest line possible. Um, and so it's probably something like this, right? Maybe it's like this. Maybe it's like this. I don't know. Maybe these are actually the same length, right? It's kind of hard to tell just by looking at it. When I saw the solution to this, I was blown away. Like the solution is so simple and so harmonious and so aesthetic. It's just gorgeous. I love this problem so much. So yeah, if you figured it out, send me an email. That's my email right there. And that's the end of the talk. So let's do some questions.
Wei, that was awesome. Thank you so much. Um, I don't know if you prefer for people to just jump in and maybe they talk over each other or to do raised hands for questions. I think either is fine with me.
I think I prefer to have people jump in.
Okay, sounds good. Then we're going to go with the anarchic approach. Um, so people can feel free to unmute and ask away.
This is a sign. There are no questions because this talk covered every possible contingency.
So you said the diagonalization proof was your favorite. What's your
Yes.
second favorite? If you were barred from using that as your example, what example would you go to?
Yeah, that's a really good question. I think it honestly might be the two dots in the line. That one is just so mind-blowingly cool. I love that one a lot. That one's like, but that might just be recency bias. Um, what else is cool? I'll give you one that a lot of people cite that I don't like. It's like square root of 2 is irrational. I don't find that one very aesthetically pleasing, but you know, math is all about aesthetic choices. What's another one? Do you have one, Max?
Well, I was going to say something that's cool about the diagonalization one, which also gets to your point about the process, is that then from then on, mathematicians use that argument all the freaking time, right? Like it shows up
Yeah.
over and over and over. Like Gödel's incompleteness theorem uses it. I used it a ton when I took complexity theory here at Northeastern. So the process was kind of the point because like it turned out that the process was useful for things that had nothing to do with the size of infinity as well.
Yeah, that's true. Diagonalization arguments in general, I think one of my favorite class of arguments. Oh, maybe infinitely many primes. I remember that one was really cool. That one's like super simple, but also like very harmonious.
I suppose I'll jump in. I want to say, um, with regard to some of the conversation, I think in part one about limitations and how e basically everything except for math is bound by reality.
Mhm.
I think an interesting limitation to math is that it is bound by human comprehension.
Mhm.
And what that means is there could be math that humans aren't equipped to understand, but like an alien species that reasons in a completely different way could be equipped to understand it. And we wouldn't even, it's like being able to see colors that you can't. It's like how, you know, there are like bees and the mantis shrimp and whatever, they can see colors that we can't see. So like you can't even begin to comprehend what it would be like.
Yeah, that's
Yeah.
interesting. I don't think that's unique to math though, right? Like your color example just gave it away, right? Like everything is like that,
Oh,
right? We can only
certainly.
think about the stuff we can think about, right?
Sure. I think that the point is simply like math is probably the like you said, math is probably the least constrained creative endeavor that exists. But
Yes,
it's worth
absolutely.
acknowledging that there's still this fundamental boundary that is even more sort of philosophically challenging than other boundaries because we can't even conceive of what's beyond the boundary.
Yeah, that's cool. That's interesting to think about. I guess I'm like less interested in that maybe because like yeah, I'm never going to be able to touch that stuff, right? So why would I worry about stuff that I just can never reach ever? Right? Math is like at the precipice at that boundary, right?
Yeah, absolutely.
I would say where we begin to worry about it is when we try to do meta-mathematical reasoning. And an example being Gödel's incompleteness theorem. When you learn the theorem, you have to first come up with some notion of what you think any mathematical system would need to have in common. And that notion inherently limits you, right? Like the notion is, well, there's going to be a finite number of symbols and everything's expressible with those symbols, and you write them down on a page, and some of them are operators, and when you start to make, I mean, they're all reasonable things to say, but nevertheless you've kind of gone from I'm reasoning about math to I'm reasoning about like human math, which is a little frustrating when you want to make a cosmically true statement.
Yeah, that's true. That reminds me of there's like a big debate on whether math is invented or discovered. Yeah, and I think from my point of view, it's actually pretty clear that it's invented, that like all of this stuff is just constructed for us, that like we want to see the world as orderly and beautiful, and that's why we make these things. And the temptation to say it's discovered is the temptation to say the universe is ordered and beautiful and structured. Whereas I don't think that's necessarily true.
I have a quick question. Thanks for the talk. Great slides. A joke question would be how long the slides took, but I won't ask that. You made a claim in this talk that really like a lot of math is beauty and aesthetics and a lot of geometric elegance and proofs, but how universal do you think that is? And do you think that's a universal thing for mathematicians, or would you say that there are others with different motivations for math?
Yeah, that's a good question. I think like, first of all, I'm not really into yodeling, right? Like some people, like not all art forms are for everyone. Um, I think math is like uniquely been stripped of its beauty. But I do like there's a part of me that wants to say it is universal, that like we as humans crave explanations for things and we seek patterns, right? That's like the deep like underlying logic of math, is like pattern seeking and problem solving and aesthetic harmony and self-expression. Yeah, I think that like kind of is a human universal thing, right? It's like the purest art.
This isn't really a question, but I was hoping to like input maybe like what gives me the tingles about math. That
Yeah.
I think what's really cool is like not even that like these axioms come out of nowhere. I actually think that it's really cool that it is like we wanted to understand like 3D space, right? And then we came up with linear algebra, and like but like that doesn't just tell us about 3D space. That tells us about like functions too, you know? And I feel like it's like actually like I don't know, I think it's like it is because of like something real that we want to understand, but then it kind of like shoots off into whatever, and then it tells us about like other things that like you wouldn't even anticipate.
Yeah,
I
that's
don't know,
like
I just think that like that's the magic for me.
yeah, that is really cool. That's kind of what I was saying. It was what I was trying to say in part 3 was like we make these tools and they start like having lives of their own and they start doing all kinds of really weird, unpredictable stuff we never could have dreamed of, right? And also like the fact that we have to start somewhere, right? Like we invented linear algebra to explain 3D space. Like ultimately we are embedded in reality, but as soon as we like the more detached we get from reality, the more like purely mathematical things get, the more weird and psychedelic things get. Yeah.
A cool example for anybody who's maybe a formal methods enthusiast here is the so-called Banach Banach-Tarski paradox. There's a really cool paper that proves it in ACL2, which is a automated theorem prover. And they start in 1 dimension and then 2 dimensions and then 3 dimensions. Like they do the unit circle in increasing numbers of dimensions. And it's wild how you can like build an intuition for this very, very, very famously counterintuitive result by looking at much simpler versions of the problem, in lower numbers of dimensions, right?
Yeah, that's right. The aesthetic of simplicity and how that
Exactly, yeah.
simplicity just like ratchets up and becomes wild so quickly. For people who don't know, the Banach-Tarski theorem says that you can break a sphere into 5 pieces and then reassemble those 5 pieces into 2 spheres that are exactly the same as what you had before. So you just like get double the number of spheres and you just break the first sphere into 5 pieces. It's like one of the weirdest things ever. I kind of want to give a talk on that, actually. I feel like I could give a pretty good talk on that.
I want to invite the guy who wrote the ACL2 paper to give a talk on it.
Oh, that'd be hype.
Okay, well, we've taken an hour of everyone's time. So I don't know if there's one more question we want to do before we close shop. Does anybody have any last burning questions they'd like to put out there?
Thanks so much for coming.
Awesome. Thank you, Wei. This is fantastic. And I'm going to post this online so people can watch after the fact if they want to.
Perfect.
Sick. Okay, bye, dude.